This is a semester 1 review. I'm going to do problems 15 to 24. In problem 15, they want you to write a quadratic function to model each graph. So I'm going to call this graph A. In order to write a quadratic model, you need to know two pieces of information. You need to know the vertex. The vertex appears to be at 2, 5. And you need to know one additional ordered pair on the graph. Well, the other ordered pair they give us is this one over here, which appears to be 4, 9. And I'm going to call that point. The formula for vertex form, y equals a, x minus h squared plus k. The only thing I don't know is a. I know hk, and I know x and y. And I'm going to plug all those into this to find the equation. So it's going to be 9 is equal to a, x minus h squared plus k. And we're going to solve that equation for a. So 9 is equal to 4 minus 2 is 2. 2 squared is 4. And notice that when I subtracted and squared, I wrote it in front of the a. And then I'm going to subtract 5. And a is 1. So the equation of the first graph is going to be y is equal to 1, x minus 2 squared plus 5. Notice when I went back and I plugged it in, I didn't include x and y this time. Otherwise, it's not really an equation. Okay, now let's go and work on the next graph that I'm going to call B. The vertex is at -1, -3. And it looks like the point on the graph is at 1, 5. So, y is equal to a, x minus h squared plus k. Now I wrote -3. You could have written plus -3. It's the same thing. Notice the minus and negative. That makes plus. So 5 is equal to 2 squared is 4. I'm going to add 3. I'm going to divide by 2. And 4, and I'm going to find out a is 2. So the equation of the second graph is y is equal to 2, x plus 1, because that's minus a -1, squared, plus k. Now let's go back and do this on the third graph. The vertex is at -4, 2. The point on the graph this time is actually the y-intercept, 0, -6. So y is equal to a, x minus h squared plus k. Now, if it helps you out, I didn't do this, but you can label these every time if you're worried that you're going to plug the wrong numbers into the equation. So feel free to just plug them, to label them every time. All right, so -6 is equal to 0 minus -4 is +4. 4 squared is 16, a plus 2. I'm going to subtract 2. I'm going to divide by 16. And I'm going to find out that a is -1/2. So the equation for the third graph is y is equal to -1/2, which makes sense because the graph opens down. X plus 4 squared, because that's your minus -4, plus k. And those are your three equations. For problem 16, we want to write a quadratic equation with the given solutions. It doesn't matter if we're talking about a quadratic equation or some higher order polynomial. If you know the solutions, i.e., if you know where it hits the x-axis, you can work backwards to write it in factored form. So this is what the solutions look like. This is factored form. Factored form is basically when you set those little equations I wrote equal to 0. That's why it says x minus 4, because you had to subtract 4 from both sides. That's why it says x plus 5, because you had to add 5 to both sides. Once you write it in factored form, now you're going to FOIL it in order to get the quadratic. So it's going to be x squared plus 5x minus 4x minus 20. The middle terms are like terms, so you get x squared plus 1x minus 20. The second one, I'm going to skip a step. The factored form is x plus 6, x minus 2. X squared minus 2x, 6x minus 12. The middle terms are like terms, and I'm left with x squared plus 4x minus 12. The third one, factored form is x minus 3, x plus 8. X squared plus 8x minus 3x minus 24. The middle terms are like terms, and I get x squared plus 5x minus 24. In problem 17, we want to solve each equation. When you go and solve this, pretend like it's any old linear equation. Even though they're not linear, they're quadratic. Pretend like it's a linear equation. You want to get x by itself. Well, the first thing you would do is you would subtract the 49. But because it is quadratic, once you isolate the x squared, you have to do this first. You cannot do this first. No, 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 no. All right, let me erase that. Now you can take the square root of both sides. But wait a second, there's a negative under the square root sign. That means that you're going to have an imaginary number. And the square root of 49 is 7, but it's imaginary, so it's 7i. Let's do it again. First, you would get x squared is equal to negative 64. Then you can square root both sides, and since there's a negative under the square root sign, and the square root of 64 is 8, you have to put I, because they're imaginary. Again, x squared is equal to negative 81. So when I square root both sides, x is going to equal plus or minus 9i. Notice the plus or minus sign, because if there's a multiple choice answer that just says 9i, and there's one that says plus or minus 9i, you have to make sure you pick the right answer. The last one, first you're going to subtract the 50. Then you're going to divide by 2. Now you can take the square root of both sides. So x is equal to plus or minus 5i. Remember that the only time you put an I is when you're taking the square root of a negative. In problem 18, I don't want you to get confused about the part that says that the answers are positive integers. That doesn't mean that you're going to write positive numbers, so just ignore that. In order to find the values of x, this is written in factored form. And yes, I realize that it doesn't have numbers in there. It has p's and q's and s's and t's. The problem is done the same way. When you have a polynomial that is already in factored form, you use the zero product property. Set each of the factors equal to 0, and then solve. Well, look at what happens here with the p. It's negative. So we're going to put plus or minus pi. P is still a positive integer because it's just, we're plugging in some number there. It's just that the little plus or minus sign in it will make it positive or negative later on. For the second one, notice that when you move q squared, it's not negative. If it's not negative, when you square root it, is it going to have an I? And the answer is no. It's just going to be plus or minus q. Let's do this again. You're going to set the factors equal to 0, and then you're going to solve for x. When you do that, s is not negative, so x is just plus or minus s. X squared plus t squared equals 0, but when you move it, you get negative t squared, so when you square root it, x is going to be plus or minus ti. My copy on my iPad of the review is a little messed up. So in problem 19, I don't know why this happened, but I want you to notice these are the first two graphs, so only focus on those. The question says, looking at the following graphs, what could be the sign of the first term and the degree of each if the polynomials are written in standard form? All they want you to do is be able to identify what kind of a polynomial it is and if the leading term should be positive or negative. So I'll call this graph A. Graph A looks cubic. So if it's cubic and it goes up from left to right, the first term would be x cubed. The second one, we'll call B, looks quadratic. If it's quadratic, it's degree 2, and since it opens up, we're going to say it's positive x squared. The next one, I'll call this one C, also looks quadratic, and it also opens up, so it's positive x squared. The last one we'll call D. Anytime a graph has an M or a W shape, it's a quartic function. Quartic means degree 4. So the question is, should it be positive x to the fourth or negative x to the fourth? W's, when it opens up, positive x to the fourth. M's, when it opens down, negative x to the fourth. In problem 20, it says find the total number of roots including complex and multiplicities for each equation. Do not be confused by the question. It is very simple. We talked about the biggest exponent in the polynomial tells you how many zeros the polynomial has. The thing is that that number includes all the real answers. That means the places where it hits the x-axis plus its multiplicities, but it also includes the complex numbers. So, in A, the biggest exponent is 6. That means it has 6 roots. B, the biggest exponent is 3. It has 3 roots. C, the biggest exponent is 5. It has 5 roots. D, the biggest exponent is 8. It has 8 roots. And E, the biggest exponent is 5. It has 5 roots. It is just that simple. Remember that some of the problems we give you, we don't explicitly tell you what to do. We hope that by reading the problem, you're going to determine what we're asking you to do. So number 21 says, Marissa's been trying to discover the secret code for a lock. After a long investigation, she discovers that the numbers in the secret code are solutions of the polynomial equation x to the fourth minus 68x cubed plus 1557x squared minus 13,770x plus 37,800 equals 0. And then, after more work, she finds that the factored form of that polynomial is what is on your screen. What are the numbers of the secret what are the numbers of the secret code? Guess what? The numbers are 5, 12, 21, and 30. Because anytime you have something in factored form and it equals 0, the solutions are gotten by the zero product property. In problem number 22, they want you to find only the real zeros of each function. You know cubic functions can have 3 roots. But not all the roots are necessarily real. So if all I want to find are the real roots, I would graph the polynomial on my calculator, and then I would find where it hits the x-axis. Remember, if you're using the TI-84, you would put this into y1 equals, you would put 0 into y2 equals, and you would find the intersection of the two graphs using the intersect function, which is probably the easiest way to do it. So the real 0 in A is 0.126. When you graph B, you should find that it hits the x-axis at 3.587. When you graph C, you should find it hits the x-axis at -3 on the nose. And when you graph D, you should find that it hits the x-axis at 2.26. Problem 23, I feel like this might have been a section we skipped, but I can't remember if we did direct variation. No, we did do direct variation. Now this comes back. We did equations that were in the form y equals kx. This was called direct variation because they were linear and they went through the origin. Well, not all direct variation necessarily is, well, no, it's linear. I shouldn't say that. So here's how this problem works. It says the number of mushroom slices that Melanie puts on a pizza varies directly as the square of the diameter of the pizza. All direct variation is in this format. So we're going to say, I'm going to call the number of mushrooms varies directly as the square of the diameter of the pizza. So from the first pizza, that ratio is going to equal the number of mushrooms to the square of the diameter of the second pizza. All right, so if she puts 30 slices on a 20-inch diameter pizza, and remember we have to square the diameter, that's going to equal, I don't know how many pieces she's putting on the next pizza, but I do know that the diameter is 16 squared. So we're going to solve that equation by cross-multiplying. Maybe it'll make you feel better if you square this first. And then we'll cross-multiply, and I'll get 400m is equal to 7680. And then we'll divide by 400, and we get 19.2. Well, you can't have 19.2 mushrooms, so it's either going to be 19 or 20 mushrooms. 24 is something we haven't gotten to, so I'm going to go over it. If you get it, great. If you don't, we're going to do it again. We don't like radicals and denominators of fractions. As a matter of fact, in Algebra 1, you should have learned how to get rid of radicals and denominators when you had a problem like 1 divided by the square root of 2. Now, what does a cube root mean? Well, a cube root is when you have three numbers that are being multiplied together. Since 8 is 2 times 2 times 2, the cubed root of 8 is 2, if that makes sense. 3 times 3 times 3 is 27, so the cube root of 27 is 3. This works for variables too. If you have x times x times x, which is x cubed, the cube root of x cubed is x. So in this problem, one of our properties of radicals says that I can start by simplifying this. That's going to make my problem a little bit easier. So 18 over 12 is 3 over 2, and y squared over y is y in the numerator. Now I'm going to rewrite this again, because now it looks a little bit nicer. To get rid of the cube root of 2 in the denominator, I need to change it so that it's the cube root of a number I can take the cube root of. Well, I can't take the cube root of 2, but I can take the cube root of 8. So if only I multiplied the number under the radical by a 4, and whatever I do to the denominator I have to do to the numerator, I'm going to get the cube root of 12y on top, and I'm going to get the cube root of 8 on the bottom, but the cube root of 8 is 2. And now my radical in, my radical in the denominator is gone. Let's try this again. I want to simplify the cube root of 3a over 4b squared c. First of all, nothing simplifies, no exponents, no bases. So I'm going to rewrite this as the cube root of 3a over the cube root of 4b squared c. Now, 4b squared c is 2 times 2 times b times b times c. In order to get rid of a cube root, I need 3 of each of them, which means that in order to get rid of the denominator, I need another 2, I need another b, and I need 2 c's. And whatever I do to the denominator, I'm also going to do to the numerator. When you multiply the radicals together, as long as they have the same root index, you just multiply what's underneath the radicals. So I'm going to get 6abc squared on top. And in the denominator, I get 8b cubed c cubed. Well, the denominator, I can now take the cube root of each of those. Hold on, let's rewrite the numerator. The denominator is 2bc. And look, the radical's gone in the denominator. All right, let's try this again. The cube root of 7xy squared over the cube root of 4x squared. You don't have to simplify it if you don't want to. You can leave this and look at this and go, okay, well, I have a 2, an x, and an x, but it's a cube root, so I need 3 of each. So in order to have 3 of each, I need another 2 and another x. And whatever I multiply the denominator by, I'm also going to multiply the numerator. So when I multiply the numerators, I get 14x squared y squared. In the denominator, I now get 8x cubed, and I can take the cube root of 8x cubed, it's 2x. And now my radical in the denominator is gone. All right, last one. The square root of 18x squared y over the square root of 2y cubed. A square root is different from a cube root. Notice it's a square root. Square roots mean I need 2 of each factor. I am actually going to go do this right now, which is I'm going to simplify this fraction because 18 divided by 2 is 9. And then y over y cubed is y squared in the denominator. Now I'm going to go back and I'm going to redistribute the square root. Wait a second. Now that I did this simplifying, I have 2 factors everywhere. The square root of 9 is 3, the square root of x squared is x, and the square root of y squared is y. And that's the answer.